So this is a video on charge, and I'll also go through electricity and hopefully household electricity in this video as well from P2 AQA Physics. So when it comes to the idea of charge, if you rub two insulating materials together, certain insulating materials, okay, they'll become electrically charged. Remember, it's a transfer of electrons due to friction that takes place. The material that gains electrons, it becomes negative, and the materials that loses electrons becomes positive. It'll have the same, so if that one's become negative too, then that one will become positive too. The two electrically charged objects are brought together, they exert a force on each other. So if they're the same type of charge, they repel. Okay, and if they have different charges, so if one's positive, one's negative, then they attract. These are all things that you know. Charges, remember, can move easily through substances, i.e. conductors, so namely metals. This leads us to the idea of current, because electrical current is the flow of charge. The size of the current depends upon two things. That's the amount of charge available and the time for it. Now normally when they do these questions, the charge can be in millicoulombs, so that's times 10 to the minus 3, and the time is going to be in milliseconds. So that's times 10 to the minus 3 as well. So you normally like to choose small values for this. You like to choose small values for this. Right, the potential difference, okay, is the voltage, potential difference between 2 points, also known as voltage, in an electrical circuit is the work done per coulomb, so work done per unit charge essentially. So that's the key thing there. Voltage is the work done per coulomb, or potential difference is the work done per coulomb, and current is the flow of electric charge. Okay? Oops daisy, circle that equation there, not very well. Okay, so some circuit symbols that you need to know. You need to know these well. So that's a switch, that's an open switch, a closed switch. There's a cell, that's one by itself. Remember, lots of cells together, a battery. A diode, diodes only allow current to flow in one direction. That's always the direction of the arrow within there, so you can see it there. Allows current to flow that way. There's a resistor, a variable resistor, so that arrow through it means that it's a variable. An LED, that's a diode that gives out light, so it's a light emitting diode. An LDR, so this takes in light, and there's a resistor in there, so it's a light dependent resistor. So the way that works is as light intensity increases, resistance decreases, so you end up with a graph like that. And you end up with the same graph for a thermistor as well, this time with temperature. So as the temperature increases, the resistance decreases, so you end up with a graph like that. So these two, the environment affects their resistance. Light for this one, higher light, less resistance. Sorry, more light, less resistance. And thermistors do with temperature or heat energy. So higher temperature, less resistance. Ammeters, they're in series, and they measure current. Voltmeters in parallel, they're wide in parallel, and they measure potential difference or voltage. A fuse, remember, limits the current that flows through a circuit. If the current reaches a specific value that the fuse is set to, the wire inside the fuse melts. And a lamp converts electrical energy into light energy. So there's some graphs that you need to know. There's a current potential difference graph, okay, and that shows how current varies with potential difference across a variety of components. The first one you need to know about is that for a resistor at a constant temperature, and here it is over here. That obeys Ohm's law. It is directly proportional. Potential difference and voltage are directly proportional. It's a straight line through the origin. That obeys Ohm's law. The resistance of a component can be found by measuring a current through and a potential difference across it. So that comes from the equation that's down here. V is equal to I times by R. Voltage is equal to current times resistance. Volts, amps, ohms. Volts, amps, ohms. The current through a resistor is directly proportional to the potential difference across it. That's Ohm's law. That's just what I've been talking about. To calculate the current from the potential difference, to calculate the current, potential difference or resistance, you need to use this equation here, which I've just been through. The current through a component depends upon its resistance. So the higher the resistance you're actually getting, the less the current. So as R goes up, I goes down. Potential difference provided by cells in series is the sum of the potential difference of each cell. So in other words, if I've got two cells and both of those are 2 volts, then that, if they're connected together, would provide 4 volts to the entire circuit. If they were the wrong way around, like this, and that was 2 volts, and that was 2 volts, that would provide 0. If I then add another one of 2 volts, that would provide only 2 volts, because those two cancel out. Okay, so let's talk about current, resistance, and voltage in series and parallel circuits. So in a series circuit, so that's one loop, remember, so things are connected in a loop, like so. There's my cell, and my resistors, very poorly drawn, but you get the idea. Okay, so one loop in a series circuit, the resistance is the sum of the resistance of each component. So if this is 2 ohms over here, this first resistor, 2 ohms, and that's 2 ohms, the total resistance will be 4 ohms, so it's added up together. The current is the same through each component. So over at the start of the circuit, it will be 2 amps, in the middle it will still be 2 amps, over here then it would be 2 amps as well. The potential difference of the supply is shared between the components. So if that was 3 volts, this could be 1.5 volts, and this could be 1.5 volts. It won't always share equally. If the resistances are different, that could have been 4 volts, and that could have been 1 volt, if that was 5 volts coming in. Right, so if they're in parallel, remember, so that's adding another loop to the circuit, like so. You don't need to know about resistors in parallel, that's A level for the AQA syllabus, but the potential difference across each component is the same. What I mean by that is not exactly what it says. It means, what it should be saying is the potential difference in each branch is the same. So if 3 volts comes out, 3 volts is across this branch here, and 3 volts is across this branch here as well. The total current through the whole circuit is the sum of the currents through the separate components. So in other words, if it was 1 amp over here, and 0.7 amps came here, then that would be 0.3 amps came there. 0.7 over here, 0.3 over here, and therefore back up to 1 amp over here. So getting back to current voltage graphs, this is a current voltage graph for a filament lamp, and this is a current voltage graph for a diode. Diodes have very high resistance in one direction, therefore they don't get a current, therefore they only allow current to flow one way. So high resistance in this direction, no current, low resistance in this direction, therefore they have a current. Filament lamps have this graph. You might need to play this part of the video back a couple of times to make sure you understand it. So, what happens here is as the voltage increases, the current increases. As the current increases, the temperature increases. As the temperature increases, the resistance increases. So it means the current can't increase as much, only a little increase. That's why it levels off. That's why you have that shape graph that you do over here. The fact that it curves like so, a curved shape like so. LEDs emit light when current flows, but remember it's got to flow in the right direction because it's a diode. As I said with LDRs, as the amount of light increases, resistance decreases, and once again with thermistors, as the amount of temperature increases, the resistance decreases, as I said before. So household electricity, cells and batteries supply DC. Okay, that's current that always flows in the same direction. So if we've got a graph, that's DC current. This will be DC current, but usually we see it as a straight line like that. That would be DC current. I shouldn't say DC current. I should say DC electricity. The first C, actually stands for current. An alternating current, so that would look like this. It goes between positive and negative, so it constantly changes direction. In the UK, mains electricity is AC. In the UK, that's 50 Hertz for the frequency, and the voltage is 230 volts. And most electrical appliances are connected with a 3-pin plug. I'm not going to spend this video going through a 3-pin plug. It's fairly straightforward. You do need to know about the earth wire, the neutral wire, and the live wire, the colours and locations of those, but you can find them quite easily on the web. The structure of electrical cable, so you've got double insulated when you see that symbol. So a square within a square. That means there's a wire around the outside, another plastic casing around the outside, another plastic casing on the inside with the 3 wires inside of there, each of which have their own plastic casing as well. Okay, so casing around the outside, and each of the 3 wires has plastic casing as well. The structure and wire of a 3-pin plug, like I said, you can find that quite easily on the web. You need to know about the position of the live wire, the neutral wire, and the earth wire, and also the fuse which sits next to the live wire. Okay, if an electrical fault occurs, it causes too great a current. So in other words, if, say, the live wire was to break off and touch a metal case, a large current will flow. So the way we prevent that from causing an issue is by using a fuse or a circuit breaker. What the fuse does is it will melt if too much current flows. What the circuit breaker does is it turns off the circuit if too much current flows. When the current in a fuse wire exceeds the rating of the fuse, it will melt, breaking the circuit. Okay, instead you might have an RCCB, which instead breaks the circuit when too much current flows. Anything with a metal case is usually earthed, because if it wasn't, then there's a chance of an electric shock. So all that means, if say here's a metal case, yep, there's a metal case, the earth wire runs off the metal case and down to ground. So if the live wire comes loose and touches it like so, then actually the metal case does not become live and protects you from electric shock. The earth wire and the fuse protect the wiring of the circuit, okay, just like I've discussed. So current, charge and power are also linked as well. When electrical charge flows through a resistor, the resistor gets hot. That's pretty straightforward, we know that. The rate at which energy is transferred by an appliance is called power. We know this from earlier on. Power is equal to energy over time. So we can do an equation for this, and power is equal to current times by voltage. Higher tier students need to know also that energy transferred is equal to voltage times by charge. Right, and that's our video on electricity and charge complete.